Hi everybody, we are going to pick up with 13.2 now, which is derivatives and integrals of vector functions. So this is going straight with picking up with ideas from Cal 1 and Cal 2 on how you do derivatives and integrals. So the derivative of a vector function is defined the same way as a real value function would have been in Cal 1. Officially, you could do the limit applied to the difference quotient. That's what this little box is right here. And so since we can apply the limit as h goes to 0 to that difference quotient, we get the same sort of derivative notation that we would have gotten back in Cal 1. Whether you call that r prime or dt, it doesn't really matter. So the vector r prime of t is called a tangent vector to the curve. So the tangent line at a point is defined to be the line parallel to the tangent vector. And so we can find what's called a unit tangent vector, where we take the derivative of our vector function r and divide it by the magnitude of r. And so if we want to do derivatives, then that's what this blue box is down at the bottom. We can have a vector function, whether it's defined in IJK notation or standard notation. We just have to take the derivative by taking the derivative of each piece inside the vector function, which could be any of your derivative rules from Cal 1 or Cal 2. And so some differentiation rules. This is very much like what it is if you're talking about stuff from Cal 1. You have the constant multiple rule. You have the sum and difference rule. That would be number 1. The constant multiple would be number 2. Number 3 is if you have a function multiplied by the vector function. So a real number function f multiplied by a vector function. That would be the product rule. But there's really 3 sorts of kind of product rules. The number 3 is the product rule, just like it would have been in Cal 1. But since we also can do dot products and cross products with vectors, then you have to have a rule for the dot product and the cross product, which they work basically like you would think they would if you were doing the product rule. And then number 6, for some reason, is the only one that the book decided to label. It is the chain rule. And so they will work very much like they would have worked if we were doing functions back in Cal 1. So for instance, sketch the plane curve, find the derivative, and sketch the position vector r and the tangent vector r prime for the given t value. And so I have my vector r as t minus 2, t squared plus 1, and yeah, that's it. Just a two component vector here when t equals -1. Well, let's find the derivative first. So r prime of t, these are just power rules. T minus 2, the derivative of t is 1. And then the t squared plus 1, the derivative will be just 2t. And so that's our derivative of our vector function. We want to figure out what happens at t equals -1. So let's plug in -1 into the derivative and into the original function. So r at -1 is -1 minus 2 and -1 squared plus 1. That is -3 and 2, I believe, if I added that correctly. And then r prime at -1 would be just 1 and 2 times -1. So I get 1 and -2. Now these things tell us stuff. And so we're going to use this to kind of sketch what's going on here. They are parametric equations, much like what we would have done back in chapter 10, if you remember that from the last section. I'm going to kind of show you kind of what this graph's going to look like down here. We're applying this when t equals -1, but we could apply what's going on to the overall curve anyway. You might remember back from chapter 10 that the original R vector here, if you have one term that's squared and one term that's linear, you're probably going to end up with a parabola. And that's true here. So let's do some t, x, and y's here, just to kind of show you what's going on. Let's do -2, -1, 0, and 1. So if I plug those into, keeping in mind that your x here would be the t minus the 2 from your vector function, and your y would be the t squared plus 1. You plug in -2, -2 minus 2 would be -4. -2 squared is 4 plus 1 would be 5. If you plugged in -1, -1 minus 2 would be -3, and -1 squared would be 1 plus 1 is 2. Notice this is r at -1. If you plug in 0, you'll get -2 and 1, and if you plug in 1, you'll get 1 minus 2, which is -1, and 1 plus 1, which is 2. So we end up with basically a parabola. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We're going over to the point -4 and up to 5, so there's a point somewhere about right here. -3, 2 would be about right here. -2, 1 would be about right there. -1, 2 would be about right here. And if you wanted to go another one, if you plugged in 2, 2 minus 2 would be 0. This will give you your y-intercept. 2 squared is 4, which is 5 if you add 1 to it. And so as we're going through time, the curve is a parabola coming down and back up. So we're going that direction. That is the curve. That's your RT vector value function there. The derivative and such tell you all sorts of things. So the R at -1 is -3, 2. That is my vector going to that point at -3, 2. So we're aiming for this point. And so we'll have a vector that goes from the origin out to that point. So there's my vector. That's my r -1. The r prime at -1, since it's technically a derivative, you would think it would be like a tangent line. And you would be basically right. It would go from that point, and you kind of treat this like a slope. The -2 is in the y-coordinate, the 1 is in the x-coordinate, so I could treat it as I'm going down to and over 1. That would give me a vector from that point down, and if you're a really good artist, that is a tangential vector, so a tangent vector. And that's how the tangent vector would look on a two-dimensional graph. And hopefully that makes some sense. So let's do another one kind of like that, except now we have exponentials, e to the 2t and an e to the t. But I'm going to do the same basic process. Plugging in 0 and then also do the derivative and plugging in 0. So let's start with the derivative. My derivative would be, since this is an ij notation, the e to the 2t would become 2e to the 2t times the I. And e to the t doesn't even change when you take its derivative, so it stays e to the t times j. And we're going to do r at 0, which would be e to the 2 times 0. Oh, left the I off. Times I. Plus e to the 0 times j. Well, e to the 0 is just 1, so you just end up with I plus j. And if I do r prime at 0, that would be 2e to the 2 times 0, I, plus e to the 0 j. That would give me 2i plus j. So that's my r at 0 and my r prime at 0. Here we end up with kind of looks like a parabola, but it's turned on its side, I believe, if we try to do some points and such. So let's try this out and see what it looks like. So we'll have some t's, some x's, and some y's. We're starting at t equals 0 for the point that we actually plugged in. So we'll just start with 0 as well. We'll do 0, 1, and 2. Remember, your x here is the e to the 2t. Your y is just e to the t from your vector function. So if you plug in 0, we already know that you get the 1 and the 1. If you plugged in, say, 1, you'll get e to the 2 times 1, which is e squared, and e to the first power on the other one. And if you plug in 2, you get e to the 2 times 2, which is e to the 4th, and then e squared. So it's not really good for looking at this, trying to figure out what's going on number-wise, because those are not very good numbers to work with. But one thing I do notice is that this x is actually e to the t squared. E to the t is y, so if I eliminated the parameter, I get x equals y squared. So I actually get a sideways parabola going this way. And I could plot points instead of t values. I could plot points like 0. What happens when y is 0? X is 0, so I get that point there. When if I plug in y is 1, x is 1, so I have the point 1, 1. When y is 2, x is 4, so I end up with that point. And you could do those points instead. But the t point, when t is 0, this t at 0, this is going to be the point 1, 1. This is the point when t is 0. So that's the point I'm going off of. So my r vector plugged in at 0 becomes I plus j. And so I'll have a vector that goes from the origin out to this point. My tangential vector, again, goes off of that point, but you'll notice with a 2 in front of the I and a 1 in front of the j, you can kind of treat this as your slope of 1/2, the number in front of the j divided by the number in front of the I. So going off of that point, I could go up 1 and over 2, which would actually be through this point. Our tangential tangent vector would do something like that. So that's the plane, that's the r prime, and sketch the position. So that's it right there. So hopefully that's not too terribly bad. Okay, we'll try one more of this type. So here we're working with e to the t plus 2t when t is 0. So for my derivative, I'll start with the derivative just like I did on the other ones. The e to the t doesn't change, so it's still e to the t times I, but the 2t becomes just 2 for the derivative of the 2t, and the j just comes along for the ride. And we're plugging in t is 0 at this point, so r of 0 is e to the 0 I plus 2 times 0 j. Well, e to the 0 is just 1, so I just get I, and 2 times 0 is 0, so the j part just goes away. If I do r prime at 0, I'll get e to the 0 times I plus 2 times j. So here I'll get an I plus 2j. Not too bad, right? So, again, plotting points on this one's probably going to be kind of bad because you have an exponential on one of those terms. So it might be nice to eliminate the parameter again instead of trying to plot the points. So let's try eliminating the parameter and see what happens. So my x is e to the t, and my y equals 2t. So I can most definitely get the t by itself on really either one of them. On the first one, I could take the natural log on both sides. So if I took the natural log of x equals the natural log of e to the t, the natural log and the e cancel to give me that the natural log of x equals t. Plug that back in up here for y, and I could get that y equals 2 times the natural log of x. And so that's a graph you might be familiar with. It goes through the point 1, 0, has an asymptote of the y-axis, and it continually goes up to the right. Since I plug in 0 for the t value, that 0 gives me the vector I, which would be at the point 1, 0. Because I have one I and no j, so the 1, 0 would be for that point. So my r vector, r at 0, gives me the vector that is literally laying on top of the x-axis pointing at that dot. The other vector, though, I could treat this as a slope of 2 over 1, which is 2. I just go up 2 and over 1 off of that point. So up 2 over 1. I'm going to go up about right here, and I'll have a tangential vector going in this direction. And that's what my plane would look like. You can do t-values if you'd rather plug in t-values, but I know what the natural log of x graph would look like, so that's a pretty easy way to do that one. Okay, so most of the problems that you're going to see is just things like find the derivative of the vector value function. And so to do that, you just take the derivative of each piece. Sometimes you do have to rewrite some things. So like for instance here, I would rewrite this as t minus 2 to the 1/2 to do the power rule. And I would write this as t to the negative 2 to do the power rule as well. That way my derivative would be to pull the power down, leave the inside the way it is, to the 1 less power times the derivative of the inside. The 3 just goes to 0, and t to the negative 2 becomes negative 2t to the negative 3. And we can simplify this a little bit. A 1/2 power with a negative on it is the same thing as a square root on the bottom. The number 0 is just the number 0, and this is negative 2 over t cubed. And that would be the derivative of that vector function. Let's do another one. Here, no rewriting involved. I can just jump in and start taking the derivative. Derivative of e to the negative t. The derivative of e to the negative t is negative e to the negative t. The derivative of t minus t cubed would be 1 minus 3t squared, and natural log t would be 1 over t. And that's pretty much it. I'll just leave it just like that. That seems like a lot of wasted space on that slide. Make y'all feel better, since we wasted a lot of space. I'll draw a bird. He's kind of angry. Okay, this one says find the unit tangent vector at the point where the given value of the parameter t, here in this case t equals 0. Remember that your unit tangent vector is the derivative of your vector that you're given divided by the magnitude of that vector, that vector derivative. And so I need to find the derivative of this. So r prime would be, derivative cosine would be negative sine times I. 3t would be 3 times j. And 2 sine 2t would be 4 cosine 2t. Okay. So that would be my derivative. Now, if you have a number to plug in, like we have t equals 0, I could go ahead and plug that 0 in, and that will help dramatically when we have to find the magnitude of our vector, because then we can work with numbers and not functions. So I'm going to go ahead and plug the number in. R prime at 0 would be negative sine 0. The 3j doesn't change. And then 4 cosine 2 times 0. Okay. Sine of 0 is 0, so this first term actually just goes away. So all I'll end up with is a 3j, and cosine 0 is 1, so I'll end up with a 4k. And so if I'm finding my unit tangent at 0, I'm going to do r prime at 0 divided by the magnitude of r prime at 0. So r at 0, I never plugged r at 0 in. I should plug that in. When you do r at 0, oh, sorry, I'm doing r prime at 0. Never mind. I read the wrong thing, didn't I? R prime at 0. Good. I was wondering why I needed the other one. R prime at 0 would be the 3 and the 4, the 3j and the 4k. So I'll have the 3j and the 4k. And I'm going to divide that by the magnitude of the 3 squared and the 4 squared. And so this will give me 3j and 4k divided by 9 and 16 make 25. So I'll end up with 3/5 of a j and 4/5 of a k. And this is my unit tangent vector at the point t equals 0. Okay, now this one tells you to find all sorts of things. If your r is t squared, and t cubed, can you find the derivative? Then can you find the unit tangent at 1? Then can you find the second derivative? And then can you find the cross product between the first derivative and the second derivative? It's a lot of things, but we could do that. That's not too bad. First of all, find the first derivative. That's really easy. So r prime at t would just be 1, 2t, and 3t squared. They're just power rules. Then if I want to find the unit tangent at 1, well, my unit tangent at 1 is r prime at 1 divided by the magnitude of r prime at 1. So I need to just plug 1 into that r above there. Plugging 1 in pretty easy. I'll get 1, 2, and 3 divided by the magnitude of 1 squared plus 2 squared plus 3 squared. That's 1, 2, and 3. Divided by 3 squared is 9. 2 squared is 4, so that's 13, and 1 more makes 14. So the square root of 14. And if you want to leave it like that, you can. Or if you wanted to make it 1 over root 14, 2 over root 14, and 3 over root 14, that works as well. But that would be your unit tangent evaluated at 1. How about the second derivative? We'll just put it right here. That's pretty easy to find. You just take the derivative of the derivative, so that would be 0, 2, and 6t. Again, just a bunch of power rules. And then we'll do the cross product of those things. So if I do the cross product of the r of t, r prime of t, and the r double prime of t, that would be, remember in cross product you have an I, a j, and a k across the top. Underneath you have a 1, a 2t, and a 3t squared from your r prime, and a 0, 2, and a 6t from your prime. So you're just taking derivatives of each one of those. So what we would have is the 2t, the 3t squared, the 2t and the 2 and the 6t get used for the I. Then we have a minus. For the j part, we would use the 1, the 3t squared, the 0, and the 6t. And for the k part, we would use the 1, the 2t, the 0, and the 2. So the first one, 2t times 2t times 6t is 12t squared, and 2 times 3 gives me 6t squared, going the other direction. 1 times 6t is 6t, and then I get a minus 0. And then I get a 2 minus 0 on the k. So this is 6t squared minus, oops, sorry, left the I off, didn't I? 6t squared I minus 6tj plus 2k. And that is the cross product between each one of those. The other vectors in the problem were written in the standard notation, so you could also say it's 6t squared, negative 6t, and 2, if you'd rather write them all the same formatted way. Okay, a little bit different directions on this one. We have a vector, and we're going to find the unit tangent at 0, the second derivative at 0, and then we're going to find the dot product between the first and second derivative. So it doesn't ask you to find the first derivative other than the part with the dot product, but you're going to need it anyway. So let's go ahead and find the first and the second derivative. So the first derivative, e to the 2t, would be 2e to the 2t. Then a negative 2e to the negative 2t. And then we have a product rule. First times derivative of the second, which would be 2e to the 2t, plus the second one times derivative of the first. So we'll have a 2e to the 2t, a negative 2e to the negative 2t, and because we're going to need a second derivative anyway, I noticed that there's a e to the 2t in common. If you factor out the e to the 2t from that product rule, you'll be left with a 2t plus 1. And in fact, since we need the second derivative anyway, let's go ahead and find it. I would have a 4e to the 2t. I would have a positive 4e to the negative 2t. And then I have another product rule. The first one times the derivative of the second plus the second one times the derivative of the first. So I'll have a 4e to the 2t, a 4e to the negative 2t. And again, there's an e to the 2t in common if you'd like to factor it out. And what you'd be left with is a 2 and a 4t and a 2. Or if you wanted to, you can simplify that to 4t plus 4. So hopefully that makes sense. Or you could pull the 4 out in common if you want to do that. There's a 4 in common on all of it anyway. But let's do the unit tangent. So I'm going to find this part first. The unit tangent at 0. That would be r prime at 0 divided by the magnitude of r prime at 0. So I just plug 0 into that first derivative that I have up there across the top, and I would have 2e to the 0, which would be 2. I would have negative 2e to the 0, which would be negative 2. And I would have e to the 0, which is 1, times 2 times 0, which would be 0, plus 1, which is 1. So we're just plugging it in and up here for all those t's. T is 0. Then I'll use those numbers to do the magnitude with. And so that leaves me 2, -2, and 1. And 2 squared is 4, and 2 squared is 4 is 8, plus 1 is 9. Square root of 9 is 3, so I'll get 2/3, -2/3, and 1/3. This is my unit tangent evaluated at 0. They also ask you to come up with what is the r prime or double prime at 0. So that's pretty easy. Just plug in 0 in for all of the part where you have on the second derivative. So you have 4e to the 2 times 0. Oops, no plus sign, that's actually a comma. 4e to the -2 times 0. And e to the 2 times 0 times 4 times 0 plus 4. So that would give me a 4, and a 4. Little things in life, I guess. I'm not really sure why that was funny, but e to the 0 is just 1, so the 4s end up showing up all the way across, and the 4 times 0 is 4. So yeah, that's kind of funny. So r double prime of 0 is just a bunch of 4s. And then for the dot product, remember your dot product is what you get when you multiply the first components and then the second components and then the third components, add them all together, see what you get. So the dot product between r prime, and notice this is t, so we don't have numbers to work with here. We'll have to do it with the functions themselves. I'll have the 2e to the 2t times the 4e to the 2t, so that's the first two components from the r prime and the r double prime. Add that to the second two components, -2e to the -2t, and 4e to the -2t. Add that to the third components, we have e to the 2t times 2t plus 1, times e to the 2t times 4t plus 4. And maybe this stuff simplifies a little bit, I'm not really sure. We'll end up with an 8e to the 4t. If you have like bases, you add your powers, and so that's where that comes from. Then we'll have a minus 8e to the -4t, adding those powers together. The e to the 2t and the e to the 2t will make an e to the 4t. And then I can just FOIL the rest of that out. If you want to FOIL it all out, you can. If you don't, it doesn't really matter a whole lot unless they just happen to combine really, really nicely. 4 times 2 is 8t squared. The outside would be a plus 4 times 2 is 8t. The inside is a 4t. And the last one is a 4. So you do have a couple of terms that could go together. This is 8e to the 4t minus 8e to the -4t. Then we'll have an 8t squared e to the 4t. The 4 and 8 make 12, so I'll get a plus 12t. Oops, I left the t off. That was supposed to be the eraser, not just a black pen. There we go. T e to the 4t. And then I'll have a plus 4e to the 4t. So the very first term and the very last term could combine together if you wanted them to. The 4 and the 8 would make a 12e to the 4t minus 8e to the -4t. And all the rest of the terms are different because of the squared on the t or the extra t that I have on the 12t. So none of that stuff will go together. And so depending on how far you want to multiply it out, any one of these would technically be correct. Nothing really combined together very nicely, but that's about as far as you could go unless you want to factor an exponential out in common. Okay, this one says find the parametric equations for the tangent line to the curve with the given parametric equations at the point. So I have an x and a y and a z. that are my parametric equations that are all given. And we want to figure out the equations for the tangent line at that point. So these parametric equations that are given is really no different than saying that I have a vector function with t squared plus 1, 4 root t, and e to the t squared minus t. And so if I want to find a tangent line, anytime you see the word tangent, you want to do a derivative of some sort. So we're going to take the derivative of this stuff. I am going to rewrite this to be 4t to the 1/2, so I can do the power rule. So my derivative, r prime, would be just a 2t for the t squared plus 1. I pull the power down and subtract 1 from the power. When I pull the 1/2 power down in front of the 4, you do half of 4 would be 2t to the negative 1/2. And then the exponential doesn't change, but I have to take the derivative of the power and put it in front. So the derivative of the power would be 2t minus 1 e to the t squared minus t. So that would be my derivative. You can rewrite that to make it look a little prettier if you want to. Not a whole lot's going to change. This would still be 2t. You could make this be 2 over the square root of t if you like, but the rest of it's just going to be the way it is. But anyway, that would be my derivative. So then I want to figure out what should I plug into t at this point. Well, I'd have to figure out what t value I used. To get this point up here, I had to plug a t value into it. And so I have to figure out what t value would work to get me those numbers. Well, for instance, t squared plus 1 is the first term of the r. The t value to get me to 2 would be positive 1 or negative 1, one of the two. I can't do a negative 1 on the square root though. So it's looking like t equaled 1 was the value I used to get that point. And you could test that across, all the way across. T equals 1 would be the correct point. So I want to plug in 1 into my derivative that I took. So I want to do r prime at 1. This would be 2 times 1, which is just 2. 2 over the square root of 1, which is also just 2. And then 2 times 1 minus 1, e to the 1 squared minus 1. That would be 2, 2, and 2 minus 1 is 1. E to the 0 is 1, so I just get 1. 2, 2, 1. That would be my vector. Now you remember when we did lines back in 12.5, we needed a vector and we needed a point. Well, now I have a vector. This would be like my vector v from back in chapter 12.5. 12.5. And then I have my point up there at the top, so that I could write my parametric equations to be x equals the point, the 2, plus the vector 2 times t. And then y would be the point 4 plus the 2 from the vector times t, and z would be the point 1 plus, and it's 1 times t, so you don't really see that 1 there, but anyway, these would be my parametric equations for my tangent line. 2 plus 2t, 4 plus 2t, and 1 plus t. So hopefully that makes some sense. Okay, we're going to do basically the same thing just to give you another example of that same sort of topic. I'm going to say that my r equation would have been t e to the negative t and 2t minus t squared. And then I don't need to rewrite anything here. I'm just going to jump in and take my derivative. So my derivative would be 1 negative e to the negative t and 2 minus 2t. But I need to know a t value that I use to plug in to get that 0, 1, 0. So using this point up here, what t value went from here to there? And this one's fairly obviously, hopefully, that if you have a t for that first component and the 0 for the first part, it's probably that t was 0. And if you did e to the 0, you get 1, and 0 minus 0, 0. So yeah, t equals 0 would be your parameter value. So I'm going to plug that into my derivative. So r prime at 0 would be 1 negative e to the negative 0 and 2 minus 2 times 0. So I have 1, negative 1, and 2 for my vector. But now I have a vector and a point. So I'd have x equals my point, which would be 0, plus the 1 times t. Y would be the point 1 plus the vector number negative 1 times t, and z would be the point 0 plus 2 from the vector times t. And I'm going to make that look a little prettier. This is x equals t, y equals 1 minus t, and z equals 2t. These represent your parametric equations for the tangent line, t, 1 minus t, and 2t. So that one worked out even better than the last one, in my opinion anyway. Okay, let's talk about integrals. The definite integral can be defined in the same way for a real valued function as it is for a vector function. You might remember our Riemann sums from Cal 2. This limit part right here, this is your Riemann sum that we did a long time ago, and said, well, actually all that area that you're finding could be represented as an integral from a to b, and we can do that with vectors as well. And all we have to do is integrate each piece of the vector, and that will be the integral of the vector function. So let's do some integrating. So this is where your Cal 2 hopefully kicks in. If I want to integrate from 0 to 2 of ti minus t cubed j plus 3t to the 5th k, like I said, I literally just integrate each piece. These are just power rules, so that's kind of nice. The t becomes t squared over 2 I. The t cubed becomes t to the 4th over 4 j. And the 3t to the 5th becomes 3t to the 6th over 6 k. And we evaluate that from 0 to 2. And so if I plug in 2, I'll end up with 2 squared over 2 I minus 2 to the 4th over 4 j. And the 3 over 6 makes a half anyway, so I'm going to go ahead and simplify this to a 2 and make this be 2 to the 6th over 2 k. If I plug in 0, since they all have t's on them, you're going to get zeros all the way across the board. You'll get 0 squared over 2, you'll get 0 to the 4th over 4, and you'll get 0 to the 6th over 2k. But this entire bracket right here is 0. The other bracket, 2 squared is 4, divided by 2 is 2. So I'll get a 2i. 2 to the 4th is 16 divided by 4, which would be 4j. And 2 to the 6th divided by 2 is actually 2 to the 5th, which is 32. And so that would be your answer. So we get a vector for our integral. Let's try another one. This one has an I component and a K component. No J component. Don't forget from Cal 2 that if you integrate 0, you get 0. You don't get a constant. So we're not going to end up with a C in any of this stuff. So if there is no J component, when we integrate it, we still have no J component. I will want to rewrite this one a little bit, though, to integrate it. Mainly because of the root t. This root t right here is really t to the 1/2. And so I'm going to multiply that across so I can do the power rule. So this is 2t to the 3/2 I. And a t and a t to the 1/2 will give me 3 to the t halves. 3/2, not t halves. 3/2 plus t to the 1/2. Okay. And so then we jump in and just start integrating. So I'll add 1 to the power, so that'll give me a 5/2 divided by 5/2 I. Then I'll end up with a 5/2 over 5/2 plus t to the 3/2 divided by 3/2 on the k, evaluated from 1 to 4. I will flip those over and multiply them, those fractions, before I plug the numbers in. So if you flip over 5/2, you get 2/5. 2/5 times 2 makes 4/5. T to the 5/2. Plus, I'll have 2/5 t to the 5/2. And a 2/3 t to the 3/2. From 1 to 4. And so then we plug numbers in. So if you plug in the 4, I'll get 4 to the 5/2 I plus 2/5 times 4 to the 5/2 again plus 2/3 times 4 to the 3/2 on the k, minus, if you plug in the 1, you'll get 4/5 times 1 to the 5/2 I plus 2/5 times 1 to the 5/2 plus 2/3 times 1 to the 3/2. Okay. So the 4 to the 5/2, the 2 on the bottom tells you to take the square root. So it's the square root of 4, which is 2, to the 5th, which is 32, times 4 on top gives me 128 fifths I. Ooh. Isn't that crazy? Anyway, so then the next one, the square root of 4 would also be 2. 2 to the 5th is 32. 32 times 2, though, is only 64. So I'll have 64 over 5. The square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16/3. Minus, plugging the 1 in is a lot easier. This is 4/5 I. This is 2/5 plus 2/3 k. And so then you just got to put all this stuff together. You have a 128 over 3, or sorry, over 5. There's 128 over 5 and a minus 4/5 on the I. Nothing on the J's. And then on the K's, I have a 64 over 5, a 16 over 3, and a minus 2/5 and a minus 2/3. So 128 minus 4 will give you 124. That's a pretty easy one on the I. The 64 over 5 plus 16 over 3 minus 2/5 minus 2/3. Whew. Let's see. You got to have a 15 on the bottom. That's pretty obvious. Let's see. This 16, 2, 5, 4, 10, 256. 256 over 15. I highly suggest that you pull your own calculator out and make sure those fractions are right. But that would be your answer, pending I didn't make a arithmetic error at the bottom. Okay, how about this one? This one probably looks more complicated, but it's actually a lot easier. These are already set up as how you would integrate it anyway. The first one, the 1 over the t plus 1, that's the rule for the natural log. This is the natural log of t plus 1. The second one, that is the rule for tangent inverse. The third one is also a natural log, but the derivative of the bottom is a 2t, so you have to put a 2 on top. That will end up pulling a 1/2 out in front of your natural log. So it's 2 natural logs and a tangent inverse. So hopefully you paid really close attention to all that stuff in Cal 2, and you know how to do all of that stuff and recognize that sort of thing. So if you plug in 1, I get natural log of 1 plus 1, which is 2. You plug in 1 on the tangent inverse. Tangent inverse at 1 is actually pi over 4. There's your little trig there jumping in at you. And then if you plug in 1 on the other one, 1 squared 1, so that'll give you a 1/2 natural log 2 on the k. If you plug in the 0, natural log of 0 plus 1 will be natural log of 1, which is 0. If you plug in 0 on tangent inverse of 0 is 0. And if you plug in 0 on the other one, you'll also get 1/2 of 0. Okay, so it actually all goes away. Now the rest of that doesn't really combine together at all very well, since they all have different I, J's, and K's on them anyway. So your answer is just natural log 2 times I, pi over 4 times J, and the 1/2 natural log 2 has the K on it. So that's not a hard one to do, but you do have to recognize your rules from Cal 2. How about this one? Secant squared t times I, t times t squared plus 1 cubed times j, and then t squared ln t on the k. Again, not terribly hard. The third one on the k is a little bit bad, but it's not awful. I guess this is the best way to say it. But we can jump in and just start integrating here. Notice this is an indefinite integral. There are no numbers to plug in here. And so on an indefinite integral, back in Cal 2, we put a plus c on there. We'll do the same thing here, but your plus c, your c will actually be a vector, not a constant, because we're doing vector functions. So we'll put a constant vector on the end. So if I integrate this, I just jump in and just start integrating. Secant squared t goes back to tangent t. Now the second part is actually a u substitution. So you might want to come to the side and just do a u sub by itself. If I was integrating t times t squared plus 1 cubed, then I would let u be t squared plus 1. du would be 2t dt. I would have to have a 2 in there and a 1/2 out in front to make this work on the integral. And so I'd get 1/2 times the integral of u cubed du. That is to add 1 to the power, which would be u to the 4th over 4. So this is 1/8 u to the 4th. But your u is t squared plus 1. So if I plug that u back in, over here I'll get 1/8 times t squared plus 1 to the 4th on that j. So a little bit of side work going on there, but nothing terribly bad. And then your next little part of side work, I would suggest doing the t squared ln t off to the side as well. This is actually integration by parts, not tabular method, but actual parts. You have to let u be the natural log of t. You have to let dv be t squared dt. And then, by parts, I would do that this integral is u times v. So I have to integrate this v. Actually, let me write that down while I'm writing this other stuff down. V would, ooh, that is awful. I hit the wrong button and made it really thick there for a minute. Your v would be 1/3 t cubed, or t cubed over 3. And your du would be 1 over t dt. And so this integral turns into u times v, which is natural log t, times 1/3 t cubed minus the integral of v times du, which is 1 over t dt. So this is 1/3 t cubed ln t minus 1/3 t squared in the integral. The t on the bottom cancels one of the t cubes. And so this is 1/3 t cubed ln t minus 1/3 times t cubed over 3, adding 1 to the power and dividing by the power. Take that as your side work up here, and I will end up with 1/3 t cubed ln t minus 1/9 t cubed on the j. And then I have a constant vector also, since it's an indefinite integral. And so a little bit of side work to come up with the second and third one, but nothing too terribly bad, hopefully. Okay, one last problem. Find the first derivative and find, I read that wrong. It doesn't say find the first derivative. It says if the first derivative is this, can we find r? So they're asking you to integrate it, and they're giving you an initial condition here. So we want to integrate the 2ti plus 3t squared j. Oh, sorry, I left the k part off. And the square root of t, which I'm going to rewrite as t to the 1/2 k. So I want to integrate this and find the c value. These are all just power rules. So this would be 2t squared over 2 on the I, or just t squared. This would be 3t cubed over 3, or just t cubed. And then I'd have add 1 to the power, so I get a 3/2 over 3/2 on the k. Plus a constant vector. I'm going to simplify this a little bit though. This is t squared I plus t cubed j plus 2/3 t to the 3/2 k plus c. I can find my c value using this little spot, this little thing right here. So then it says, if you plug in 1, you get I plus j. So let's plug in 1. That would be 1 squared I plus 1 squared j plus 2/3 times 1 to the 3/2 k plus c had to be I plus j. Well, this is I plus j plus 2/3 k plus c. If I were to subtract the I from both sides, they end up canceling. And if I subtract the j from both sides, I accidentally wrote an I there, but I meant to put a j. If you subtract the j from both sides, they will also end up canceling. Remember, you're solving for the c here. If you subtract the 2/3 k over, though, you'll get that c is negative 2/3 k. And that's my c value. Put that into my integrated part, and so I know r of t is t squared I, t cubed j, 2/3 t to the 3/2 k minus 2/3 k. Or, since there are multiple k's in there, you could factor the k out, and that's usually what happens when we try to simplify this thing. We will write it like this, where we take the 2/3 t to the 3/2 and subtract the 2/3 off inside. And so this would be your answer for your integral. So hopefully that all made pretty good sense. That is the end of section 13.2 then.